Let's see. Okay, so I'm recording. So um, some of you have taken my grad class before, some of you haven't. That's okay. I think most of the people in the class are doing linguistics or language education of some kind. Um, there are a few people who are doing other things, and that's okay too. One of the reasons that I and doing this class is that when I learned statistics, I think a lot of the textbooks and videos and so forth, a lot of them are really geared towards medical research. And that's fine and it's good, but sometimes it can be kind of difficult to see how do we use this in linguistics or education. So I do have a lot of my own personal examples that I'll be giving. One thing that we're going to use throughout the course um, is this web page here. We'll use it a little bit for educational purposes, but the tool is here as well. However, what I would like for you to learn throughout the class is enough of the basic ideas and concepts that you don't need to rely on the website all the time, but it is useful. I use it sometimes. It's pretty convenient. So I am going to start today with a couple of uh, basic ideas. We'll get right to it. Uh, by the way, if you have any questions in the middle, please stop me and ask your questions. I'd rather you figure things out as we go along. So you might notice I've got this whiteboard here because we are going to do a lot of calculations, okay? And I do want to draw some images and things along the way. I kind of self-titled this class Breaking the Black Box because what we mean is in statistics, increasingly, we have what's called the black box, which is basically you put some data into the computer does some calculations, they're a mystery, and it gives you some numbers. And in general, that's what we want. Everyone wants to know what these numbers are. That will help us to solve our problems. Personally, I hate black boxes because I always think, uh, what's going on in there? Really? Can I trust it? Whether you have that same feeling deep in your heart or not doesn't matter to me, but I am going to teach you what's going on in a lot of these tests because if you understand what's going on inside of this black box, if you understand what kind of calculations the computer's doing, this will really help to prevent you from choosing the wrong test. This will help you to understand how to interpret these numbers. This will help you to make sure that your research is going to go well, that you've got the right test, that you understand what are the good and bad points about your test, and how far you can take it to your conclusion. So um, I am going to start with one other kind of controversial sentence right at the beginning, which is I would like everyone to remember that um, statistics is a very good tool. It's a very useful tool. It helps us check the reliability of our data. It helps us be a bit sure about what we're doing. But actually, the controversial sentence is that statistics doesn't actually prove anything. What statistics does is gives you evidence towards your conclusion. However, statistics alone is not enough. What I mean is you have to have some reason why you're doing the statistical test in the first place. The statistical tests usually help give us evidence that our conclusion is true. It's very strong evidence, but you still need the backing concepts behind it. There's very famous examples of, for example, correlation does not equal causation. Global warming has been going up each year. If this is global warming and this is number of pirates, every year as global warming increases, the number of pirates decreases. Or maybe I should draw that backwards, but all I'm saying is this does not mean that global warming is causing a decrease in the number of pirates, nor does it mean that having fewer pirates makes global warming increase. Before I even do a statistical test, I should have some kind of reason that would make me think that these things are true. There's no reason to think that the number of pirates has anything to do with global warming, so I would never do the statistical test in the first place. So you do require your common sense, but you do also require some theory. There has to be a reason that you're running the test. Otherwise, you'll maybe be victim to some of these very strange tests or results. However, correlation does not equal causation. That's a famous thing that a lot of people like to say. But why do we test it? Why do we use the statistics? Because if there is a good reason to think these things go together, and there's a very strong correlation, that's very strong evidence that it probably one is causing the other one. We still need to use our brains to figure out which one is causing which, or if there's some secret thing that's causing both of them at the same time, but it is very strong evidence. Also, if you suspect that there's causation between A and B, if you do an experiment and there's no correlation does mean that there's no causation. It's impossible to have causation without correlation. So, that doesn't mean that statistics doesn't tell us anything, but it does mean that before we run statistical tests, we have to have a good reason why we're taking data. We have to have good theory behind what we're doing. I would like you to put that into your head because that's going to be an important point in what we talk about today. Okay. So there are a few underlying principles of statistics. Okay. We need a reason for doing any tests that we're going to be doing. I don't know if you guys can read that. You'll need some kind of reason for doing anything that you're doing. The second thing is to remember that when we're doing a statistical test, there are some different types of statistics. In this class, we're mostly going to be talking about, I can never spell it, something called Gaussian statistics. And I'll explain what the difference between that is and some other ones in a little bit, but I would like you to just remember this term, especially I think we have a couple of medical students. There's another, I don't remember if it's E or A, but there's another type of statistics called Bayesian statistics that is getting more and more common in the medical community. So if you're doing medical research, they might require you to do some Bayesian statistics. We use it sometimes in language and linguistics research education, but before you can understand Bayesian or Bayesian statistics, Gaussian is also called classical statistics because it's the one that we've been doing most of the work in for the longest time. So it's a good idea to have this idea first. One of the principles of this Gaussian statistics, the man who named it or founded it was Gauss. That's the reason it's called Gaussian. Bayesian statistics, the man or woman, I don't know actually, who first invented it was named Bayes. That was their last name, so that's where the names come from. For Gaussian statistics, one of the ideas is that anything is possible. Okay, um, anything is possible, but what we're trying to find is what is probable. So actually, Gaussian statistics, as well as Bayesian statistics, as well as really any statistics, what we're dealing with is probability at the end of the day. Um, what is the probability of this being true? What is the probability of this group being larger than this group, etc., etc. Okay. Um, so when we're doing statistical tests, especially with Gaussian statistics, we should be dealing with a scenario where anything is possible, okay, but probably not uh, probable. Okay, so if you're ever running into a situation where I tested 700 people and 0 said yes and 700 said no, okay, you might not want to do a statistical test at this point. If you really have 0 people and 700 people, you're probably looking at this as an impossibility. For example, you shouldn't run statistics on what is the percentage of non-smokers who smoke. By definition, non-smokers do not smoke, so that's not possible. So we can't use any kind of statistics there, really. Similarly, how often do I don't know, serial verbs appear in English? That's an impossibility in English, so the number is always going to be 0. That's not a problem of statistics. That's not something statistics can help us with. Okay. Now, it can be something that has a very low probability, and that's fine. But the reason I bring this up later, when we do some tests and some calculations together, you're going to see that if you ever run into a situation where your data is 0, that's technically an impossibility. If you feed an impossibility into the model, it will, or into the statistical test, it will kind of break the test, or the test will be equal to a 100% chance or something like that. But theoretically, nothing should ever be a 100% chance when we're using, especially Gaussian statistics. It should be a 99.999999999% chance, which we usually interpret in our human brains as a 100% chance. But following this idea, following this system, we should always accept the idea that there's always a very small chance that we're wrong. And as a scientist, that's actually a pretty good standpoint to have. That doesn't mean we always have to change our opinion, but if someone has very good data, that's very different from ours, then we should always entertain the idea at the very least that we could possibly be wrong. Okay. So for Gaussian statistics, anything is technically possible. Well, but what we're really interested in is it probable? So if we have a theory that X is probably true, we can collect data, but the data isn't always 100% clear. Actually, that's true in any kind of science. In linguistics and language education, actually, the father of modern linguistics, Noam Chomsky, he said linguistics is psychology because it lives in the human brain. And so, by that definition, yeah, if you're doing linguistics or language education research, it is psychology. What that means, though, is that humans have a lot of variation. No two humans are exactly the same. They learn the same English or the same Japanese, but they might speak it differently. If you're trying to teach them a third language or a fourth language, what works for one person might not work equally well for another person. But that's actually the same with biology. If I take medicine, the medicine might work better for some people than other people for a number of different reasons based on their weight or their height or their sex or etc. etc. With molecular chemistry, even hydrogen atoms usually have one neutron, but sometimes some of them have two. Why? No one's really 100% sure, but even with molecular physics or molecular chemistry, nothing is ever 100% clean. So statistics helps us to see, even though we have some amount of random variation, even though two people are not the same, even though taking the same medicine doesn't have exactly the same effect on them, can we say that overall the medicine had an effect? Can I say that overall my class helped people to learn this language? Can we say overall that Japanese speakers tend to do this more than English speakers, etc., etc., etc.? Even considering the variation in people, can we see that there is a trend? Okay, so it helps us discover what is probable. The example that I often give with this, and if you were in my grad class before, my apologies, you've probably seen this, is, sorry, let's see, the imagine that you have a coin, and you suspect that the coin might be rigged. The rigged coin scenario. Okay. If you suspect that a coin might be rigged, this means heads more than tails. Let's say I go to a casino and I want to gamble some money, but I suspect that the casino is cheating. They have a special rigged coin that will give more heads than tails. How many times do I have to flip the coin before I can be pretty sure that this coin is rigged or cheating? Okay. This is the kind of thing that statistics helps us to do. It helps us to make a decision based on the data that we observe. What is the probability of this coin being rigged, for example? So if you flip the coin one time, and the first time you get, heads, okay, I think we can all agree that's not enough times for me to think that this coin is rigged. Okay, yes, it came up heads, but if I flip a normal coin, there's a 50% chance that it will be heads, right? If I flip it again and it's tails, well, this is a pretty normal thing to happen, right? But what if I flip it again? What if it's 5 heads and 1 tails? Is that enough times? And is that a big enough difference for me to be sure that the coin is rigged? I don't know. I mean, at this stage, it's 5 heads and 1 tails that could happen. That's not such a crazy thing. If it came out 75 heads and 25 tails, I think most of us would agree that this is a strange coin. It's highly improbable that a fair coin would be 75 heads and 25 tails. However, when it's 6 and 1 or 7 and 3 or 28 and 19, it's kind of hard for humans to make an objective call is this a rigged coin? Is it not a rigged coin? So statistics helps us to do that. So the next concept I want to deal with, let's take this rigged coin problem. Okay. I want us to think about now what we have here. What is the probability of a coin landing on heads? For a fair coin, it should be 1/2, right? That's the idea. If I flip the coin 2 times, what is the probability of getting heads 2 times? If I flip a coin 2 times, there's 4 possibilities. It could be heads 2 times, tails then heads, heads then tails, or tails 2 times. So in this situation, the probability of getting heads 2 times is 1 divided by 4. The probability of getting 1 heads and 1 tails, if I don't care about the order, is 2 divided by 4. And if the probability of getting 2 tails is 1 divided by 4. Okay. If I make a graph of this, okay, what is the probability of 2 heads? There's 1 chance of that. Heads and tails, there's 2 chances for that, 2 out of 4. And for all tails, there's 1 chance of that. That's what the chart looks like. Okay. Let's take it one further. What does it look like? What if I flip the coin 3 times? If I flip the coin 3 times, if it's a fair coin, what is the probability of me getting 3 heads in a row? We can draw it out, but the formula for this, if it's all heads, how many ways can I get heads? There's only one way to get 3 heads. It's 1 divided by, the way we write this, I'm flipping the coin 3 times. I don't know if anyone remembers this from algebra, but 3 exclamation point. This means 3 times 2 times 1. Okay. Or I'm sorry. No, I got it wrong. I'm sorry. It's 2 to the 3rd power. I'm sorry. This is the number of different possibilities. There's only 2 possibilities, heads or tails. And I'm flipping it 3 times, so it has to be 2 times 2 times 2. So 1/8. If I draw this out, I can have heads, 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 tails, heads, 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 tails. You can kind of imagine, if I draw it out, there's now 8 possibilities. Okay. My 3rd time of flipping it, it could be heads, it could be tails. Okay. So this is my proof that this is going to work for you. So now that I draw it out, there's only one way to get 3 heads. So 1 divided by how many possibilities are there? 8. 8 is equal to 2 times 2 times 2. The way we looked at it before as well, when there were 4, when I flipped the coin 2 times, it was 2 to the 2nd power, which is 4. So now if I draw this graph for 8 times, it looks like, sorry, for 3 flips, it looks like this. There's one way to get all heads. To get 1 tails and 2 heads, there are now three ways to get one tail and two heads. There's also one, two, three ways to get two tails and one head. And there's one way to get three tails. Okay. If I flip the coin four times, I'm going to run into a similar thing. I'm going to cheat a little bit and kind of give you the answer here, but let's see, this side's easier to see for you guys. If I do it four times, okay, now I'm going to have 16. There's 1/16th chance of it being four heads in a row, 1/16th chance of it being four tails in a row, four chances of one tails. Sorry, I did not do this the best day. Need a little bit more. There we go. Okay. For all tails, for only one heads, for two tails, okay, etc., etc. Well, what you might start to notice, and sorry I didn't draw these in the best order that I could have, this makes a pattern where in the middle we have the most possibilities. If I draw a line, it makes this curve kind of like this. This is what is called the normal distribution. That does not mean that it's normal in terms of not strange. This means that for any random event, if it is truly random, I'm going to have the thing that is most probable in the middle, the next most probable on the sides, and as I get towards the edges, I'm going to have things that are less and less probable. The more times I repeat this, the more data I take, this becomes less and less and less probable. If I flip a coin two times and I told you I got heads twice, you would probably believe me. It's not so strange. There's a 25% chance of that happening. If I said I got three heads in a row, that's a 1/8 chance of something happening. That's still a 12.5% chance. That's not so strange. If I say I flip a coin four times in a row, okay, that's 1/16th of a chance. That's about an 8% chance of that happening. It starts to get less and less believable the more times I flip the coin, right? But it doesn't mean it's impossible. It just means that it's improbable. If I flip a coin 10 times in a row and told you I got 10 heads in a row, you would probably not believe me because it's very improbable. It's not impossible. It's very possible to flip a coin 10 times and get heads 10 times in a row, a very fair coin. But the probability of that happening is very, very low. It would be 1 times 2 to the 10th power, which, if anyone has a calculator with them, oh, I did not get the best calculator for this. So 1 in 1,024 chance. Okay, a very, very low chance of getting 10 heads in a row. Does that mean it's impossible? No. If everyone in the world was asked to flip a coin 10 times tomorrow, some people in the world would probably get 10 heads because there's billions of people in the world. However, most people would not get 10 heads. So, again, going back to the first thing I said, or sorry, the second thing I said today, with statistics, we're dealing with the world of not impossible, but what is highly improbable. Okay. So this normal distribution is going to be very important because when we want to compare two groups later, or when we want to compare things later, we will often look at this normal distribution uh, what is the chance that I pulled some data that was a little bit to the side? If I flip a coin uh, 10 times, what is the chance that I got 10 heads versus what is the chance that I got 5 heads and 5 tails? Okay. One of these is a pretty normal thing to happen. One of these is not a very normal thing to happen. And so uh, a little bit later, I'm going to bring this back, okay, and show you how this relates to what we just talked about. But please remember this normal distribution. Anytime you have truly random events, they tend to follow this curve or this pattern. Okay, and this curve helps us to understand what is the probability of some data that we have taken. Okay. Small note, there are some instances where data does not follow this curve. In that situation, there are special considerations. We will get to those later. But for now, this is a thing that happens in normal life. It's a Shizen Gensho, a naturally occurring phenomenon. Right. Okay. All right. So I'm going to erase this for a moment. Okay. I'm going to leave just one graph because now we're going to learn the first test of Gaussian statistics, quite famous test. I don't use it very much in my own research. I have used it before, but I really like this one because it's not so difficult and it's a great way to show you exactly what we're talking about here. Okay. The test we're going to learn today is called the chi-square test. Okay. If anyone uses the Serbian alphabet, you're probably laughing at me. This is supposed to be a chi. This is not actually X. This is the Greek letter chi. This is read chi, not chai. It's an embarrassing mistake I've made before, but I mostly learned through reading. So forgive me that. But yes, it is called a chi-square. Um, the chi-square test is used when we have counts of data. We have something called nominal or categorical category data, usually used when I'm counting how many times something happens. Okay, even with number data, there's different kinds of number data. So if I ask boys and girls yes or no, and I ask one boy and he says yes, and I ask another boy and he says no, and I ask a girl and she says yes, and another girl says yes, and yes, and yes, and no, and yes, and etc., etc., etc. Okay, so one person's data is not a number. One person's data is either a yes or a no. If you're doing corpus linguistics, how many times does American English or British English use the phrase hey versus hello? You can count how many times you found the word hey. You can count the number of times someone said hello. You can do it for American English and for British English. That's an example of a place where you might use chi-square in linguistics or language education. Or if you have a very, very simple experiment design, if you have students and you want to find out did, I don't know, your first period class or your second period class read the textbook more. So you ask them, did you read the textbook, yes or no? It does not have to be yes or no. You can also have other categories, such as maybe, and you can, I don't know, you can have another category if we're going to be if we're going to be 21st century about this. Or this can be first period class, second period class, third period class, fourth period class, heavy smokers, somewhat heavy smokers, light smokers, non-smokers. Okay, you can have lots of different categories. It doesn't matter. Most people usually start with 2 categories, so that's what we're going to start with. Okay. So if I go and take some data, okay, if I ask some boys and some girls, yes or no, have you ever had a surgery before? Yes or no? Or that's a medical example. But if I want to know about for linguistics, do you usually use よね? そうだよね, よね. Do you use this when you're speaking Japanese and you ask them a simple yes or no? Yes, you do. No, you don't. Okay. Or if I'm testing them to see if they say it in a role playing, yes, they said it. No, they didn't. Okay. And I'm comparing boys and girls. In a perfect world, I would get 50 boys and 50 girls. Okay. But we all know that the world is not perfect. So I might have 57 boys and 43 girls. That's the way research happens sometimes. There's actually slightly more girls in the world. So even if I asked every single boy and girl in the world, I still would not have an even number. We can look at percentages to give us a good idea of what percent, and then I can compare them quite evenly. However, still, I need to know, are these percents really different? Okay. Why would I think that it might not be different? Okay. Remember our coin flipping example. Okay. If 2 people flip a coin, okay, 4 times, and one person gets exactly 2 heads and 2 tails, and another person gets, I don't know, 3 heads and 1 tail or something like that. Okay. Both of these things are pretty probable. There's a pretty good chance of either of those things happening. So can I be sure that this person's coin is different from this person's coin? In this case, both of those things are quite probable. It's not so strange to flip a coin 4 times and have 3 heads, or to flip a coin 4 times and have 3 tails instead of 2 and 2. That's not such a strange thing to happen. Okay, so how do I make the decision? If you flip a coin 4 times and I flip a coin 4 times, and we suspect one of our coins is rigged, okay, how much difference do we need to have in your coin and my coin before we know that these are different? How much difference between yes and no of boys and girls do we need before we can say, yeah, boys and girls are probably different? Okay, a very small difference like this, okay, this is probably due to what's called sampling error. Okay, this error does not mean that you made a mistake. Okay, this error means that anytime, here is the world of randomness. Randomly in the world, if you ask 50 boys a question and you ask 50 girls a question, there is a chance that accidentally you're going to get some boys on this side, or you're going to get too many girls on this side. If you flip a coin, if you flip, I don't know, 10 different coins, 4 times each, they're not all going to be in the middle. By chance, you will have some coins here and you will have some coins here, probably. Okay. That's what we call sampling error. Okay. So we want to know, is the difference bigger than the sampling error? For Gaussian statistics, the big difference between Gaussian statistics and other kinds of statistics is we have a underlying assumption. The idea is that we are going to take a sample. there is some perfect world true distribution. Okay, I don't know what it is, but I want to, if I take a big sample, if I take a sample, it should look quite similar to the real sample. Okay, so what I mean is if you flip a coin 4 times, if you do that with 100 coins, okay, most of the coins are going to give you 2 heads and 2 tails, but some will give you this, some will give you this, a few this, a few this, very few will give you these. Okay, that's sampling error. But if I do this with 100 different coins, I should have, I don't know, maybe 3 coins, 5 coins, 12 coins, 50 coins, 12 coins, 5 coins, 3 coins that do this. Something like this. If I do it with 1 coin, if I do it with 10 coins, if I do it with 100 coins, 200 coins, this shape is not going to change. So with Gaussian statistics, what we're doing is we take a sample from the real world. We assume that the real world probably looks like this. Okay? And so when we take our sample should look something like the real world curve. So if we get a big enough sample, the sample should look enough like the real world curve that we can make some guesses about what the real world curve looks like. Within a little bit of error points. Okay. So this is the way that Gaussian statistics works. We did not flip every single coin in the world. We flipped 100 coins. That should be enough that we should see we should see some kind of distribution that is very similar to what happens if you flip all the coins in the world. So I cannot ask every boy and every girl in the world. It's impossible. But I can ask very similar boys and girls the same question. And if there's a large difference between them, okay, I should be able to see that, okay, the boys' normal distribution is here around this average, and the girls' distribution is here around this average. Yes, sometimes boys are higher than girls, but usually girls are higher than boys. Okay, this is my sample data, but if my sample data looks like this, I can guess that the real world curve looks pretty similar to what I've got. Okay, that's kind of the way it works. So if I'm asking boys and girls, yes or no, I will get a little bit of sample error. It's unavoidable. This is the way the world works. I'm randomly asking some boys and girls. Maybe it's inside of an experiment, but there's always randomness. I try to get only Sendai boys and only Sendai girls. I really want to control as much as I can, but there's things that I cannot control for. Even Sendai boys and Sendai girls, there's some inherent differences in them. How much money their parents made, what age they started to speak. There's lots of different things that might affect if they say yes or no. I can't control for all of them, so instead I use statistics and I accept the fact that some boys are going to be on this side, some boys are going to be on this side, some girls will be on this side, some girls will be on this side. Okay? But overall, what can I guess about boys in general and girls in general from this sample that I have taken? Right. So let's run the test. Okay. Let's run a chi-square test. When we're running a chi-square test, just like any of these tests in statistics, what we actually do is we start with something called a null hypothesis. Okay. Now, if you're ever reading research papers, people don't normally write. People don't normally write. My null hypothesis is da 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 da. because that's a very standard thing to do. Everyone knows this, everyone understands, so we don't always write it. But null hypothesis is the backwards or opposite of basically your hypothesis. Okay. So I want to know, girls, are girls equal to boys in the number of times they said yes? Okay. I don't know the answer to this, okay, question. The null hypothesis is always going to be that there is no difference. That they're the same. That they're the same. I'm sorry. That should be this. The null hypothesis is there is no difference between these two. They're exactly the same. Okay. The reason we do this is that it's quite difficult to give evidence for something to. It's quite difficult to give evidence for this to be 100% true, but it's quite easy to give evidence for some idea is completely false. Okay, I'll show you why in a moment. But the null hypothesis here is that there is no difference between girls and boys. Okay, and then we're going to do a test and see if this null hypothesis is correct or incorrect. Now, I said correct, incorrect, but actually, again, we're not testing whether this null hypothesis is correct or incorrect. We're testing whether or not it is probable or highly improbable. Remember, statistics should always say there is a possibility I'm wrong. However, you do get to a point where it's kind of ridiculous to believe that the null hypothesis is true. And that's what we're looking. Okay, first let's start running this test. Okay, the way this works, if I have a null hypothesis, okay, I can think about what should be true, what is true, and what should be true, if the null hypothesis was completely true. Okay, so let's start with some fake data here. Okay, let's pretend that boys, girls. Can you see that? Okay. Yes. No. Okay. Let's say that 75 boys said yes, 25 boys said no. I don't even know what the question is, but 25 girls said yes, and 75 said no. Okay. Are these groups the same? Okay. So I'm going to make my null hypothesis that the girls and the boys are the same. There's no difference between these groups. That's always the null hypothesis for these kinds of statistical tests. Now, what I need to do in order to find out how true this is I need to think about what should be true if the null hypothesis is true. Okay, the formula for a chi-square, I'm going to give it here and I'm going to explain it. Chi-square is equal to I'm going to explain this to you, and then we're going to do it. As we go on, I'm going to explain how to read all these Greek symbols, because that will also help you when you're trying to learn other tests in the future. So the chi-squared is equal to the sum of, O stands for observed. What is the data that you observed? What is the data that you got from your sample? That means 75, 25, 25, 75 for us. Okay, versus the expected. Expected means what would the sample be? What would be true if the null hypothesis is true and there is no difference between these people. Okay, you're going to subtract those, square it, and then divide by the expected. Okay, now this I means that we need to do it for each one of these. So in our case, we have two groups and two answers. So boys and girls, yes and no. Okay, so we're going to need to do it for this 75, this 25, for this 25, and for this 75. And we're going to use this formula 4 times, and we're going to add all 4 of those together. That's what this means. This means sum this, add it all together, and the I means to do it for each one of them. In the future, we'll run into some formulas where you're not using an I and it's some fixed value. That's what the I is for. The I is to tell you that you need to do it for each one, and we need the observed for this box and the expected for this box, not for a different box. Okay, so the observed values are already here. We know what they are. What is the expected value? How can we find that? Okay, let's think logically for a moment. Okay, how many boys are there in total? Okay, now you might notice I made some easy to calculate numbers here, but I can add them up here. There are exactly 100 boys. Okay, and how many girls are there? There are exactly 100 girls, right? How many people said yes? 100 people said yes. How many people said no? 100 people said no. Okay. How many people did I ask in total? I asked a total of 200 people. Okay, so if you're doing a chi-square, the first thing that we usually do is add these up these ways so we can find out how many boys were there, how many people said yes. Okay. Now, the formula for finding the expected, okay, is going to be basically a percentage. Okay, so we want to find this, we want, there should be 100, there's 100 boys out of 200 people. Okay, so this big one divided by this one times, okay, how many people said yes? 100 out of 200 people said yes. So 50% of people were boys and 50% of people said yes. So I expect 25% of all of the people to be a boy who said yes. That's what I expect. Okay, 100 divided by 200 is 1/2 times 1/2 equals 25%. Okay, we can multiply that by the total number of people, 200, to find if there was no difference between boys and girls. Half of the people were boys and half of the people said yes. If there was truly no difference between boys and girls, I would expect 50. That's how many people I would expect. I would expect to have 50 boys who said yes. Okay. By logic, I think you guys can see there's 200 people. If there's really no difference between these groups, half of them said yes, half of them said no, half of them are boys, half of them are girls. We expect 50 for each of these, right? Okay. If I want to do this chi-square test, then what I need to do is, okay, go to this box. So my observed value is 75. My expected value is 50. So 75 minus 50. And I need to square that divided by the expected value, which is 50. Okay. This sum means repeat this for every one of these boxes. So then my next one is 25 minus 50 squared divided by 50 plus, now this one, 25 minus 50 squared, divide by 50, and the same thing for this one. Okay. Now there's a couple of things to notice here. Let's look at this first one. We have 75 minus 50. That's 25. Okay. 25 squared is a very big number, 625 divided by 50. Okay. This gives me, let's see. This gives me 12.5. Okay. Now, in this case, more people than I expected were boys who said yes. This is a greater number than what I expect if there is no difference between boys and girls, if that null hypothesis is true. Okay. The very nice thing about this is I don't care if the number is bigger or lower than what I expect. The higher that is, okay, the more I expect. The farther the number is from my expectation, the more I think that this null hypothesis is probably not true. So the nice thing here is 25 minus 50 is negative 25. Okay, but if you remember, negative 25 squared, this is negative 25 times negative 25. That's the same as positive 25 times positive 25. This equals the same as positive 25 squared. It's the same 625 divided by 50 again. It's going to be the same 12.5 again. So one of the reasons we use this squaring, okay, is because I don't care if the expectation is, I don't care if my data is higher or lower than my expectation. I just care how different it is. So using the squares helps to make sure that I'm looking at how different it is, regardless of whether or not it's positive or negative. Okay. So if I add these all together, okay, if I continue, that would be 12.5. I made this beautiful data set, so it will be 12.5 times 4 is going to be 50. So my chi-square would be equal to 50. Okay. Now, this problem, I did this way, okay, so that you can see very easily, very clearly, okay, how this works. Okay, so I want to see how different are my actual values. How different are they from what it should be, what I expect, if the null hypothesis is true. Okay, and as you might guess, the larger that the the chi-square value is, the larger it is, the less probable it is. Okay, I can tell you from experience, we probably have a p-value of 0.000001. Okay, probably we have a 99.999% chance that there is a difference between boys and girls. Now, is that a 100% chance? No, it's not. Statistics does not deal in the world of 100% chances. Okay. However, a 99.99999% chance, okay, it would be ridiculous to say, oh, it's probably not true. Okay. That's what statistics helps us to do. We start to deal with the world of what is highly improbable. Okay, so yes, it's possible that boys and girls are exactly the same, and I took this data. However, the chance of me taking this data, this much data, and getting these results, if there's really no difference between boys and girls, is extremely low. It's extremely improbable that this would happen. Okay, so that's a very, very, very good, strong evidence that these two groups are probably not the same. Okay, Um, so now I want you guys to do one. Okay, this is a simple one. We're going to kick it up a notch. Okay. Uh, I use these nice, beautiful, easy numbers. Okay, because it's very easy to calculate. It's very easy to see. Okay, but now what I'm going to do, let's take, okay, let's pretend, okay, I asked some boys, same 75 said yes, 34 said no, okay, 64 girls said yes, and 12 said no. Okay, the last one I think is really easy to see, 75% of boys versus 25% of girls. Clearly that's a huge difference. Okay, but in this case, both of them have a higher percent chance of saying yes. Is there a difference? This is much more difficult to use your intuition and just guess about. Okay, so let's do the same thing. I'll get you started, and then I want you to complete it, and I'll type it into the Google chat as well, just in case you're having difficulty seeing. Okay. So the first thing I want to do, okay, is how many boys were there in total? Okay, so 75 plus 34, that's what, 109, I think. And how many girls were there in total? It looks like 76, right? Okay. So I don't have the same number of boys and girls, but that's okay. I still have data from quite a lot of people. How many people said yes in general? That's going to be 139. Okay. How many people said no in general? That's going to be what, 46? Okay. So, how many people were there in total? I'm not going to give you that. Okay. I am going to remind you how to get the expected value of boys. Okay, we need to know what percent of people do I expect to be boys who said yes if everyone was the same, if my null hypothesis is true. So remember the way to do that. I showed you the proof, but let's remember. Okay, it should be what is it? Boys divided by all times yes divided by all. Okay, that gives you the percentage of boys who probably said yes. And then if you want to find the number, this is going to be the percentage, but we want to find the number. We have to multiply that by the total number of all people. Okay, so let me write that in here for you. Okay, just in case. Boys divided by all times yes divided by all times all. Okay, that's the formula for finding this box. Okay, if you want to find this box, it's the number of boys divided by all times the number of no divided by all times all. Okay, see if you can do it. See if you can find the expected values for all of these. Okay, then 75 minus whatever this is, square it and divide it by whatever this is. Okay, I'm going to write in the chat. You can show your work, and then I would like you guys to solve this problem. You can go ahead and start solving it if you're ready to solve it, and I am going to write in the chat in case you can't see very well. Sorry, hold on. Yeah. I'm going to give you guys, so we're not just all going free for all. I'm going to assign some of these to you when you find it. Please write it. Let's see. When you find those, write them in for me. And since you were so quick, I'll leave you with the final one. When you've got some of your answers, please write them in there. Is your name Khadija? Am I getting that right? Or is there a different name I should call you? Or is my pronunciation horrible?
Yeah, that's right. Yeah, it's
Okay,
Khadija.
and you're giving me E 0.18 for which value? For the total chi-square?
No, no, no. This is the expectation. I thought you were asking first about the expectation.
Yeah, I
Oh,
did, and then you were so quick that I decided to, in the chat, I gave everyone some problems.
oh,
Uh,
really?
yeah, sorry, I should have explained. Yeah, you were very quick. What you've got there, she did very good. What you found is you found 0.18. That's the percentage that I would expect. But before you put that in the
yeah.
chi-square, just multiply it by the total number of people, which, who knows the total number of people?
It's 185.
Yeah, exactly. Right, very good. So, how are we doing? Christina, are you there?
Yes, I am still working on it. I'm so sorry that I'm
No,
very
it's okay.
slow.
It's okay. It's okay. It's okay. It's no problem. Take your time. Take your time.
So I am looking at the previous formula that we used. So
Uh
if we
huh.
have 75 boys who said yes out
Uh huh.
of a total of 185 people,
Mm-hmm.
and then we have 109 boys in total out of 185 people. Am I on the right track?
Uh, yeah. So we have 109 boys
Yes.
divided by 185 people. That's right. And
Yes.
we're going to multiply that by the number of people who said yes, which is 139,
Oh, okay.
divided by 185. Right. In the last time's example, by chance, not
Mm-hmm.
chance, I gave a very easy to calculate example. The number of yeses and nos were even, but in the real world, there's a good chance. I mean, depending on what your question is, more people said yes in general. So the percentage of yes is much higher than no for everyone.
I
Anyway,
see.
so the percentage of boys who said yes, uh, we're not curious in the percentage of necessarily boys who said yes. We're curious about the percentage of people who were both boys and who also said yes. So the way to
I
get that
see.
is like that. And then once you find the percentage by doing this, you simply multiply it by the total number of people, which is 185.
Yes.
Do you have a calculator?
I don't have it nearby. Just
Oh
one second.
no. Okay, good. Yeah, so the boys who said no is 30.5%. Good. Well, let me help out. So if this is 0.305 or 30.5% times 185, okay, we should get something like, let's see. Okay, let's see. Boys who said no, let's see. I'm getting, for this one, 46 divided by 185 times 109 divided by 185. I'm getting 14.65%. Can you double check? Let's see. May. We've got, let's see. Girls who said yes. So people who said yes is 139. Sorry. 139 divided by 185 times girls was 76 divided by 185. Okay. For girls who said yes, I'm getting also a much lower number. Okay, I think some people are getting confused. You're finding the percentage of girls who said yes. I don't want the percentage of girls who said yes. I want the percentage of people who were girls and who said yes. There's a lower number of percentage of girls anyway. So the girls is never going to be 50% because less than 50% of all people are girls. So to get this expected value here, okay, we need to get the girls. The number of girls was 76. Yeah, you can ignore this number for right now. For the expected value, we don't actually use this number. There's 76 divided by the total is 185 times how many people said yes was 139 divided by 185. So I should get 0.30, let's just say 87. So about 30.87% of all the people were girls who said yes. That's what I'm looking for the percentage here. If I multiply this number by 185, the expected value here should be, if there was no difference between boys and girls, if they said yes and no at the same rate, I would expect there to be 57.11 girls who said yes. Of course, it's impossible to have 0.11 girls, but this is the math. Okay. So Christina, yes. That's not a percentage though. That's the actual number. So you've got 81.89. Right. If the number of boys and girls who said yes and no was even, okay, I would expect there to be 81.89 boys who said yes. Okay. Notice that this boys number is going up, while the girls number is going down. That tells me that there was probably a higher percentage of girls who were saying yes than boys. Okay. So I should see something similar but backwards here. Okay. Let's see. Boys who said no. So we've got 109 divided by 185. Whoops. 109 divided by 185. Okay, and then the people who said no is times 46 divided by 185. Okay, so there should be about 14.65%. And when we multiply that by 185, I'm getting 27.10. Okay. So in order to get this box here, we need to take the number of boys, which is 109, divided by all people, 185. I'm going to multiply that by the number of people who said no, 46, divided by the entire number of people is 185. Okay, that should give me my percent. Then I'm going to multiply that by 185, which is my grand total here. All of these together comes out to 27.10, I think. Okay. Girls who said yes formula is 76 divided by 185 times 139 divided by 185. Right, exactly. Yes, very good, May. It should be 0.31%. And when you multiply 0.31 times the total number of people, 185, that equals this. That's correct. Very good. And let's see. Girls who said no. I'm running out of space here. Let's see. Girls who said no should be 46 divided by 185 times. The number of girls was 76 divided by 185. Okay, if I want to find this expected value, I need to multiply by 185 again. Okay, so let's do that really quickly. And that should be 18 point, let's just call it 18.9. Okay, so in this way, I can see that if there was truly no difference between the boys and the girls, I would expect a few more boys to say yes and about the same percentage backwards to say no. I would expect a few more girls to say no. Oh, sorry, a few girls to say yes and a few more girls to say no. Okay, but how far is that really from my observed values? Okay, very good. So now what we need to do, okay, just like we did last time. Now we have the blue number and the red number in each box. Okay, so sorry if this is a little bit difficult to read, but yeah, we need to come in here and 75 minus 81.89, square it, and then divide by the red number, which is what I would expect if there's no difference, 81.89. Okay. Figure that out for each box, and then add those four values together. We're getting close to the end, but the basic idea is I'll give you a little bit of cheat help, and then I'll give a practice problem for you guys to work on. Let me flip this around. Let's see. So we've got we should have, for example, in box number 1, 75 minus 81.89 squared divided by 81.89 plus the next box is going to be that, what was it? How many boys said no? What was it? 34? 34 minus what was it? 27 point, 1, something like that, squared, divided by, 27.1, okay, plus, same thing for the girls. So the girls who said yes was, what was it, 64, I think, minus 57 point something, I don't remember, but bear with me, divided by the same 57 point something, plus the girls who said no was 12, and if they were the same as the boys, I would expect there to be 18.89 girls. And adding these four things together, that's what this big letter here means. Okay, back when we had the formula. So the sum of means I'm going to add all of those things together. And actually, I did this calculation already. At the end of the day, this chi-square comes out to be about 5.6867. Okay, that's the chi-square for this. Okay, that's how far are the observed values from the expected values. If these two groups were truly even, if they said yes and no at the same percentages, how different is my real data from what I would expect if there was no difference? And that's my chi-square value, which is 5.6867. Okay. What I do there, from there, the next step is to find what we call a p-value. The p-value is the probability. What is the probability that I would get a chi-square this large if they were the same? Okay. The way to do this is usually statistical calculators do this, but there's one other piece of information you need. You need to know what is the chi-square, and you also need to know something called the degrees of freedom. This is usually written df. For a chi-square, the degrees of freedom is the number of groups minus 1 times the number of choices minus 1. So we had two groups, boys and girls, minus 1 is 1. So 1 times, how many choices did they have? They had two choices, yes or no. 2 minus 1 is 1. So 1 times 1 is 1. I had 1 degree of freedom. If there were more choices, if there were 3 choices, yes, no, maybe, then I would have 3 minus 1 is 2. I would have 2 degrees of freedom. Okay. Then there is a chart. I've drawn it for you here. It's a little bit difficult to see, but the more degrees of freedom there are, the higher that I expect the chi-square value to be, because the more boxes that I have to add together. So if there were 3 choices, I would be adding 2 more boxes. And the more numbers that I add, of course, the more that the higher the chi-square value is going to be. Each of these numbers, because I'm squaring them, they will never be negative. It will always be positive. Okay, so we include the degrees of freedom because that tells us where do we expect chi-square to be in a normal situation. Okay, and that changes a little bit, but what you can see is if the degrees of freedom is 1 or 2, it looks like half of a normal distribution. When the degrees of freedom get bigger and bigger and bigger, it looks like a normal distribution. Near degrees of freedom 5, I expect my chi-square to be around 5 if there's that many different choices. If there's degrees of freedom of 3, I expect the chi-square to be around 3 for a very natural thing. Okay, it's not so strange for that kind of thing to happen. But for 1 and 2, it almost kind of looks like half of a normal distribution, and that's more or less what it is. Okay, so you can use calculus to find exactly where on this line, if my chi-square is 5.6867 and my degrees of freedom is 1, okay, you can see it's going to be somewhere around here on this line. Okay, this is the probability or the p-value. Okay, the lower the p-value is, the more I can trust my data. This p-value is what is the chance, okay, that in a normal world I accidentally drew a sample that had this much of a difference, even though the real world sample is not like this. Okay, so what is the chance that my chi-square would be this big if the real world values were not this big? Okay, if in the real world, if they were the exact same, what is the chance that I would pull such a thing? As you can see, the p-value here is going to be very, very, very low. Okay, you're probably familiar. What is a good p-value? In social sciences, language testing, and so forth, we usually use p of 0.05. Okay, indicating that there's less than a 5% chance that I had too much too much sampling error. If I took more boys and more girls, there's less than a 5% chance that they would be very close to each other. Okay, now this p-value, it's going to be different for different fields. Okay, in language education and social sciences, a lot of times we use p equals 0.05. In medicine, they often have a much stricter p-value, but it also depends on the circumstances. Okay, think about it this way. If there is a headache medicine, and if I tell you there's a 5% chance that the medicine will not help your headache, and there's no side effects, and there's a 95% chance that it will help your headache, and there's no side effects, most people want to take that drug. And in that case, I think medicine, they would also probably use p as 0.05. Not a problem. If I want to know, in my class, I tried 2 ways of teaching, one with a whiteboard, one with a PowerPoint. And if I'm 95% sure that the PowerPoint worked better, or that the whiteboard worked better, it's kind of ridiculous to say, they were the same. If I'm wrong, the penalty is not so big. There's not such a problem in being wrong, and in fact, I want to do the thing that I'm most sure of. If we are talking about medicine killing you, then that's an entirely different thing. Most people don't want to risk a 5% chance. If I said this medicine, it has a 5% chance of taking away, it will take away your headache, but it has a 5% chance of killing you. Most people don't want to take that medicine in that case. So what is the acceptable p-value? It's kind of case by case. We have some medical students, so I did mention that. But for a lot of language research, a lot of times we use p as 0.05 because it's with a 95% chance that or greater, it starts to get pretty ridiculous to think that no, these two groups are the same. Okay. So in this worked example, okay, you can see that from the beginning, it's not really clear, in my humble opinion. If you gave me this data and said, are the boys and girls different? I would say, yeah, I don't know. Even if you change them to percentages, I don't know. It's kind of close. Okay, so the statistics can help you to do this. Okay, I know we're going over. I'm sorry, I'm almost done. Let me show you just really quickly, and then I will put something on the Google Classroom for you guys. Okay, so I'm going to shrink this slightly. Whoops, that's not looking for. That's what I'm looking for. Okay, so sorry guys, bear with me for a moment. All right, so I'm showing you my web page and where you can get a chi-square test if you need one. is there is this one here. Is there a difference between groups? Okay, this is the first one we did today. Okay, for use for data that is based on counting, non-numerical answers or observations. Okay, so if we click here, it will ask you how many groups do we have? We had 2 groups, boys and girls. How many possible answers or options were there? There were 2, yes or no. And if we put these into the calculator here, okay, it should give us something very similar. Okay, yeah, it rounds to 2, but I said 5.689, and so yes, that rounds to 5.69. That is the chi-square value. The total number of people is 185, and the p-value is 0.02, which means it's lower than 0.05, which means, yes, there's probably a difference in these groups. Okay. It does also give you an effect size. We are going to talk about that in the future when we talk about correlation, because that's highly related to correlation. All right, so when the p-value is less than 0.05, okay, or for different fields it might be different things. Okay, the stupid joke is if the p-value is low, you reject that hypothesis that is null. Okay, you reject the null hypothesis. I cannot believe that these 2 groups are the same. It's too much of a difference. There's a 98% chance that they're different. It's starting to get ridiculous to think that these 2 groups are the same. Right? So it doesn't prove it 100% outright. That's not something statistics can do, but it can get us very close to the answer. That's very big evidence. If I also have some theoretical reasons to believe there's differences, and I take this data, that's a very strong argument that, yeah, these boys and girls are different as to whether or not they say yes or no to whatever the question is. Okay, so basic idea of this test and all the ones that we'll do in the future. How far different is my actual data from what I expect the data to be if there's no difference? Okay, that's how this kind of difference testing works. So this is the chi-square. I'm going to give you some practice problems. I'm going to put this video onto the internet so that you can do it before next week. And then next week, we're going to move to a different kind of hypothesis testing, very similar, but for different kinds of data. Okay, I'm going to stop the recording here, and then if there's any questions,